think several of you came up and had some helpful comments after class, and I do appreciate those. And so I've incorporated a little of that. We're not going to go over the non-enzymatic Maillard reaction again, but I just want to make sure when we're talking about browning, there's essentially two types, right? There's the non-enzymatic, which we kind of talked about already. But under the non-enzymatic, we talked about caramelization a little bit. But it has a browning. We talked about how it does turn brown. Well, that is a non-enzymatic browning. It's a heat reaction. And the same with the Maillard reaction. So these are two types of browning, of non-enzymatic browning. We're going to talk now about enzymatic browning. We kind of started that before. So that's non-enzymatic. Now we're on enzymatic browning. Clearly that means it requires an enzyme. And there are several enzymes that work browning. There we go. And but they're all polyphenol oxidases, and usually they require a metal. The most common would be copper. So I drew it for you before, and my TAs tried to help me out and correct me a little bit, and they were correct. I drew the circular bond. That's what you were trying to tell me, wasn't it? There wasn't a circular bond. Okay, so in the phenolic compounds, the phenol, some type of phenol, and we say phenolic compound because there's a lot of them. And so this is like a generic phenolic compound. And it's got the OHs on it, which is what makes it the phenol, right? And then with oxygen, that's probably the most important part, is that this enzymatic browning requires oxygen, so therefore it is an oxidative reaction. It's an oxidation. And what else is oxidation? What's another word that we can call this oxidation reaction? Aging, senescence, ripening. It's us. Oxidation, the wrinkles in my skin, all of these things are oxidative processes. I am oxidizing before your eyes. Now you can go on the computer and you can actually click on a YouTube that's 32 minutes long that will show you an apple once it's been cut oxidizing. And you can have it on your screen and just watch it for it takes 32 minutes for it to fully, pretty cool. Anyway, so this is enzymatic browning, and we talked about, let's finish it. Okay, so this requires the enzyme, and I before just put up there enzyme. And several of you came up to tell me what the enzyme was. I appreciate that. So I wasn't trying to go that deep, because there are a lot of people, not a lot, there are a few people in here who haven't had any chemistry in college. They are not necessarily chemistry majors. They are in here for a different reason. So I didn't want to, but we're going to do it. If you guys want to know it, we're going to do it. So there. So the most common metal for this will be copper. But others work. Believe me, silver. Other metals also can be cofactors. But it's a copper polyphenol oxidase. Again, a generic name. It's not even naming the polyphenol. And then we get this sort of orthoquinone. But this is how we get to our quinones. And again, we talked about how these quinones have other functions in your metabolism. Phytoquinones, this is vitamin K. So there are a lot of them. And this, when I drew before, I drew the benzene ring, and I drew this in here. And the teachers were trying to tell me, well, girl, that's not right. And they were right. So the bonds would be like this. We wouldn't have 3 double bonds anymore. Okay, so that circle is gone. All right, and now it's a series of steps that you don't have to know to where we get to melanin, which is the brown pigment. And this process, by the way, is called melanosis. Latin, osis, condition of browning, melanin, browning, condition of browning. All right, so the rate at which this occurs is directly proportional to the amount of polyphenols in the food. Remember we talked about it's the cracking of the walls that opens up those polyphenols. They've been protected before, but when you cut it, you have opened up those bubbles that hold it. Think of continuous, discontinuous phase. All right, and so now we've got these polyphenols that are being exposed to oxygen and this enzyme. So it is the amount of polyphenol in the food that controls the rate of browning, i.e. apples. Apples and pears, but apples more specifically have the highest polyphenols, and they are the ones that are going to brown the fastest. This is essentially oxidation of food. And we talked before about the apples, pears, bananas, eggplant, and by the way, someone mentioned avocado at the end of class, and I don't remember now, but avocados are in this group too. Avocados undergo enzymatic browning, not the Maillard reaction, not non-enzymatic browning. All right, so avocados are in the same group. They undergo enzymatic browning. Now, y'all, I don't know if there's ever been, I remember at the University of Florida, this is all they talked about. This was in the 80s. All they talked about was enzymatic and non-enzymatic browning, and because that was the time when we were starting to really, really understand, or maybe just me, that we were trying to feed a world that was becoming overpopulated and there wasn't going to be enough food. What on earth would, in the browning, why would food scientists care? It's because statistics show us that 50%, write this down, 50% of our produce is lost due to enzymatic browning. 50%. So do you think food scientists care about how to control enzymatic browning? You bet they do. And I am telling you, even though this was being brought up, not being brought up, this was being studied furiously in the 80s, it is still a huge, huge thing. For example, how do we control this enzymatic browning? I'm going to write over here. First, I think we should talk about the beneficial aspects of this. Some of the good things that it's not all bad, this enzymatic browning. For example, coffee. The color and flavor of your coffee is due to enzymatic browning. Write that down. These are the good things. Benefits. Coffee, flavor, color. Dried fruits, figs, raisins. They are all that color and flavor because of enzymatic browning. So it's not all bad. However, the bad stuff is all of the fruits and vegetables that go bad due to oxidation, enzymatic browning. How do we control it? So some of the ways that are being experimented with, and we're doing this in our lab when we make guacamole, is acid. So let's use this and apply this to guacamole. Okay? So the acid is the what when you add to all guacamole? Did anybody add tomatoes? Yeah. I add tomatoes to my guacamole too. Chopped up tomatoes. Is there acid in a tomato? Yeah, you better believe there is. So we're changing the pH. How about chelation? If we can bind, what does chelation mean? Binding to metal. So if we can bind the copper, we can shut this sucker down, can't we? So how do we bind? What would you do if you were trying to chelate the copper? What would you add necessarily? Protein. Did you say that, sir? Thank you. You were thinking that. I felt it. I felt these vibes. All right, so chelation would be add some source of protein that would bind. So let's go back to our guacamole. Is there any protein in lime juice? No. Fruit is solid carbs. Is there any protein in tomato? Absolutely. For every half cup of tomato, 5 grams of carbs, 2 grams of protein. Just a little bit of protein. Maybe not enough. Maybe the guacamole I make, because I use a lot of tomato, is not going to go as brown as the one you make when you don't use tomato. You see what I'm saying? So the amount that you use may impact. All right, other things that that you can use would be blanching. Blanching means you get your water boiling and you throw the vegetable in there for about 30 seconds and take it out. I do this all the time when I'm having parties and I want to make a great crudité, or a big vegetable tray. I will blanch like green beans and red pepper strips, 30 seconds in hot water, then you pour it into ice cold water and it gets this bright color and it's crisp and you haven't changed any nutrient value. It's a beautiful party thing if any of you want to go there. But anyway, the point is, This blanching denatures the protein, and the enzyme is probably a protein, right? So hopefully, again, that can have an impact, and the amount that you do, that you blanch, may have an impact. But it's not enough. Food science is working really, really hard. By the way, just out of curiosity, how do we control non-enzymatic browning? Go back to that. How do we control that? If I asked you, what was the control mechanism for non-enzymatic browning, what would you guess? Considering that non-enzymatic browning usually requires heat. So couldn't we control non-enzymatic browning through controlling the temperature? There you go. All right. This is why many of us keep our non-fat dry milk and different things we don't want to get brown. We keep them in the freezer. I keep mine in the freezer. All right, but as far as this one, all of these things you can see, even in, yes, sir.
I just had a question. So
I assumed.
You gave an example of cake mix going brown over years. Is that enzymatic or non-enzymatic?
That's non-enzymatic. That's Maillard browning. And even though that doesn't require heat, remember we mentioned the one exception that not required heat would be at room temperature for long periods of time. Thank you. Thank you for bringing that up. Yes?
Does exposure to oxygen also affect, or if you kept it like vacuum seal, would that last longer?
Okay, are you talking, which one are you talking about? Enzymatic or non-enzymatic? I don't know that oxygen would necessarily have an impact on non-enzymatic brownings. Oxygen is not a factor. It is the reducing sugar and the amine, the protein. Yes?
So when you see these cake mixes, they always say store in a cool, dark area.
That's why.
Have any?
That's why.
So the dark area. Like,
Oh, the light action.
or is that just?
I don't know. I'm not sure. That's a very good question. I know that it's controlling the temperature. I think that if you have it in a dark temperature, then they're assuming it's going to be cooler. If you have it in a very bright temperature, one would assume it's going to be warmer. But the exposure to light is a good one. I'm not sure. Yes. Oh, okay. I'm sorry. All right. So let's move on. So we're still on this enzymatic browning. You guys, this is the last one is genetic engineering. And as you can imagine, this is where most of the work is going right now. And there is a product called the Arctic apple. Anybody heard of that? The Arctic apple. And genetically, they are doing gene splicing, GMOing, and they are putting in little genes that reduce the amount of phenols in the product. This is where food science is going, is reducing the amount of these polyphenols in foods so that the browning doesn't occur and they last longer. Yes, ma'am?
Do they not smell as nice?
Thank you. I was hoping somebody would ask that. That is a great question. Because the flavor and the smell of many of these are due to the polyphenols. So are we impacting? In my opinion, yes, but that is subjective. Has anyone ever had an Arctic apple? No. Okay, look for them. Look for them. You might find them in, do sprouts carry GMOs? They may not. So you might have to get it at a Safeway or something, and they may not be that available yet. I've had one simply because I've been in UC Davis. Do you ever go to picnic day?
It's always on Cal Day.
Yeah. Oh, it is? You know what? Your band always comes to our band contest. We have a big band thing, and anyway, at the Mondavi Food Science Center on picnic day, they always open that up, and there's an experimental vineyard there. There's all kinds of experimental foods, and they're part of the Arctic apple experiment. And so I got to taste, when you go there for picnic day, you get to taste all the stuff they're doing. It's really cool. You get wine, you're walking around. Anyway, because they make wine around campus. So anyway, so if you ever get around, that's the only time I've tasted it. But look for it in the store now. You know that it has been genetically engineered to have less polyphenols in it. So if you cut it open, it should not brown like another apple. And I would love to hear your opinion on the flavor, because, and in fact, Katie, what you asked me about, that really is, we're talking about, here's that word again, organoleptics, aren't we? I hope you guys are getting that word down. I've said it about 10 times in this class. All right. That's one of the most important things that food scientists do, is deal with the organoleptics. So I think that's all I wanted to say about browning. We spent a lot of time on it because in food science, it is probably one of the most important reactions, if not the most, that food scientists deal with, is the two types of browning. And just understanding why it's happening has taken decades. And so it's fairly important that you get that. Seems like I wanted to mention something too about Dr. Maillard that I forgot to tell you guys before. No. All right, yeah.
Quick question, so with controlling browning, are you talking about the phenocopper or the enzyme?
What now?
Do you control the phenol or the enzyme?
You mean in the genetic engineering? They're genetically engineering the amount of this, the amount of phenols. There's less phenols to work on. Now her question was, are they altering the amount of this, or are they altering the amount of this in the product? Do you think that? I think that's a very interesting perspective. Which one could you modify? Could you possibly modify this, the amount of this that's available, instead of this? Wouldn't that be easier? I don't know. I'm not a geneticist. There must be some reason that they're attacking the other one first. It's very interesting. Yes, sir?
Is the copper naturally burned
Is copper what?
Is the copper
Absolutely. The minerals that we get, most of them we're getting from our fruits and vegetables through the soil. This is an environmental nutritive support system. So that's why many of the countries that I work with who are copper deficient, iodine deficient, these are environmental deficiencies because their soil doesn't have it. So absolutely the copper is present, yes.
I made baked pears last Friday, and what I did to control browning is I cut them in half and put them back together just to reduce browning.
Okay, you put it back together to reduce browning. What did that do? Exactly, and that's what the seed in the avocado does too. Okay, it imitates a whole fruit. All right, we need to move on. I love you have questions. This is so awesome. You guys are great. But we do need to move on with the material, okay? All right, so let's get to now, how do we measure? How do we measure sugar solutions? Clearly, this is pretty important to food science, how much sugar is in something, because we have to be able to control browning. Should we expect browning? Think of all those. I gave you 8 or 9 different functions of sugars in foods. Clearly, we need to know how much is in there so we can control the impacts of these functions. So there are 3 mechanisms, machines, that do this. The hygrometer, the refractometer, actually refractometer, hygrometer. Kathleen, I just got back from Texas, y'all. Not Texas, Florida, but I mean, all my relatives there are originally from Texas, so I mean, you know what they said to me? Oh, Kathleen, I haven't seen some of these people in a long time. I said, Kathleen, you sound like a Californian. You're not even talking with a Southern accent anymore. All right, so all of these things essentially are met here. Water, how is light refracted, how the flow properties, okay, the continuous, discontinuous phase. Those of you in the lab, we've done a lot with flow properties. So these 3 things are used, however, they all, once these numbers, we get numbers from each of these. And in fact, the concentrations, the sugar concentration, let me do it that way, the sugar concentration, because that's what we're measuring, the sugar concentration in the solutions, all of these measurements are converted to something that we call the Brix value. And this is usually written in the literature as BX, big B, little x. The Brix value. And this Brix value, there are actually 2 people who worked on this, and one of them was Dr. Brix. And I don't know how the 2 of them are decided that his name got to go on it. Anyway, all right, so it does sound pretty cool, the Brix value. But this is essentially a scale that measures the percent of the sugar concentration in a solution. And solution is SOL, that's what I usually abbreviate. So when would the Brix value be used? That's rhetorical. I always hated teachers who did rhetorical questions, but I'm one of them now. The Brix value is used to make fruit juice, wine, your Coca-Cola. It's used largely in the beverage industry. That's the main way that we use Brix. Well, this Brix value was used. Believe me, the people making Coca-Cola, do you guys remember when Coke decided to redo their old recipe and come out with a new Coke? Do you remember the uprising in America? I've never seen us more united. I think that's the last time I saw us really united, was over the old Coke recipe. And they had to come back with the classic Coke. They had to bring it back. You know what they changed? The Brix value. The new soda had a lower Brix value, and this country raised hell. They didn't know what they knew. All they knew is they didn't like the flavor. So they went back to classic, which has a higher Brix value. Isn't that interesting? I find it interesting. Now, would something with a higher Brix value be sweeter or less sweet?
Sweeter.
Absolutely, absolutely. All right, so when you guys get down on Coca-Cola or some of those products out there, industries who are trying to make change to be healthier, you remember that. You remember that McDonald's introduced the McLean. It was probably before y'all were born. Remember the McLean? It was McLean, the McLean. McLean, get it? She's sitting there going, yes, it'd be in one. So it was a burger that would use 97% fat-free, homegrown beef. No one ordered it. It came in a whole wheat bun, everything. Just me. I would be driving through with my little girls. What happened to clean, please? Oh, you're gonna have to pull up over there. It's gonna take about 20 minutes because it's in the freezer. We'll bring it out to you. This is McDonald's. And then it became, well, we're not carrying it anymore because no one here eats it. Do you know where they sell McLean's? Europe. Oh. You can go to Switzerland and get one. You can go to France and get one. We're in London, but you can't get one here. Isn't that interesting? So again, when you sit here and accuse the food industry, make sure that you understand there are big giants like Coke and McDonald's. McDonald's in the world, food giants. And they have introduced healthier changes to this country, and they've been rejected. Because these companies are out to make money. They're not altruistic. So we in food science have to find ways of acceptance in this country. All right, let's go on. So, examples of sweeteners that we've already done. You should have this down. Sucrose, glucose, fructose, lactose, and maltose. These are all normal sweeteners in our foods. We talked about carbohydrates before. Basically, I was teaching you what they were and how they were in mainly the disaccharides like milk and wheat and barley and malt. But these, now we're talking about specific sweeteners that we use. And sucrose, glucose, fructose, lactose, and maltose are all sweeteners that are used individually, independent of their disaccharide structure. Another source of sweeteners are our syrups. Syrups are pretty big in the food industry. More specifically, which syrup, you guys? Absolutely. Corn syrup. And corn syrup is used quite a bit. Corn syrup, by definition, is a byproduct of cornstarch production. And in the food industry, here you go, this is going to answer so many questions for you. In the food industry, we call this byproduct of cornstarch production dextrose to make sure we differentiate it is different from glucose. It is a byproduct of cornstarch. It is dextrose. So we call it dextrose. And basically, this is a very viscous liquid that consists of 75% sugar plus 25% water. This is so common in the food industry that we now have something called dextrose equivalents. And food is measured, this is all, clearly this is produced food, isn't it? This is food that is produced, that is used dextrose, okay, this corn syrup stuff. And these dextrose equivalents are used to measure the power of the dextrose in that particular sugar. And dextrose equivalence is defined as, by the way, we call this DEs, Get it? Dextrose? All right, see if y'all are awake. Okay, and this is, are you ready? The number of reducing sugars in the product divided by the total number of glucose molecules. And then you multiply this by 100. And that is your dextrose equivalence. Clearly, this is something that someone has to do in a laboratory setting to be able to measure this. The reducing sugars, most commonly, this would be like your maltose, any kind of dextrins. Remember what dextrins are? Dextrins. Those are those little strands. Remember, the shorter they are, the sweeter. The longer they are, these are the kind of things that food scientists are measuring. And these dextrose equivalents become very important. Let me give you an example. I have one here. Where's my dextrose? Here we go. If a sugar has a dextrose equivalent of 100, it is completely converted all starch to glucose. That this production process has converted all the starch that was there to glucose. And that is a dextrose of equivalent. And it's not good or bad, it just is. And it's used by food science for different products. A high conversion corn syrup. So in actual science, high conversion corn syrup, this is how it's abbreviated, has a DE of, it's got to be greater than 58. It's got to be greater than 58 to be considered a high conversion corn syrup. A lot of information, I know. We're going to move on. Okay. So moving on to other. Yes, sir. Go ahead. No, go ahead.
Yeah. So is dextrose just glucose, or there is like a?
No, it's glucose. It's glucose, but it's different in that it from a food production. This designation is to let us know this is coming from corn syrup.
And then in the equivalence, so when it says total number of glucose molecules, we're counting the ones inside the starch as well.
Yes, sir. And honestly, I've never done this. This is sort of out of my range, quite frankly. This is food scientists in a laboratory setting that I read about it too. Okay. So moving on to other nutritive sweeteners. I appreciate you guys letting me move so fast. I know there's a lot of things that are interesting and we'd love to discuss. And I hope at some point we get to do that. All right, so moving on, we're still in nutritive sweeteners, correct? All right, so we're now to another nutritive sweetener called honey. I'm gonna have to pay him at the end of the semester, you know that. To react in all the right ways. All right, so honey. Guess who makes honey? Bees, yes. All right, you're gonna love this one, you guys. I love this little fact. Do you know to make 1 pound of honey, 1 pound of honey, and yes, we're still using the American way. 1 pound is how many ounces? 16 ounces. 1 pound of honey requires 1 million, oh, excuse me, 2 million flowers. A bee has got to get the nectar equivalent to 2 million flowers, have 1 pound of honey. I love that little fact. I could just see the little bee buzzing around, making sure it's measured up. It's, okay, I'm up to 1.5 million now. All right. And the plant, so these are just one little facts here. The plant that the bee gets the honey from determines the flavor. All right. You go to Florida, and all along the roads are these just Honey here, honey here, honey here. It's a big honey state, as you can imagine, because there's a lot of produce. Well, California's a big honey state too, and it has all the bees left. I'm not sure why, but the point is that if it takes the nectar of 2 million flowers, do you think these little bees are out there going, I'm only going to orange blossoms. That's it. I'm going nowhere else. I'm restricting myself to orange blossoms because we're making orange blossom honey. And I'm going to make sure that I only get nectar from orange blossoms. Okay. Now, how can we make sure that our bees only use orange blossoms for their nectar? Surround them with nothing but orange trees. And that's why these producers put these bees in groves, in different places. They're trying to control where they get their nectar, so they can sell it as orange blossom honey. But do you think that they can 100% control that one little outlier bee that's decided to go forth to another plant? I think of that movie, Ants, what is it? Not Ants, but A Bug's Life. I love that film. I love that little guy. You know, I have a lot of simpatico with him. And he goes off to another land. Well, can we control that one bee? So can we say that orange blossom honey is 100% orange blossom? No. All right, this is one of the reasons that honey must be identified in that list for people with allergies. And people who are on allergic medication or on hypertensive medication, I always recommend do not get honey. Because I cannot guarantee to you that there is not a plant in there that you don't have an allergy to. Do you understand this? Very, very important. We can control to a degree if the poor bees are in nothing but orange blossoms, right? But you can't for sure 100% say one little bee did not go somewhere else. And it might be a very productive bee. You never know. They could be bringing back excess honey. So you've got to be careful about the plant. So the third point would be many plants. Many plants, let me put apostrophe there, nectar, could be in one honey. In one honeycomb, essentially. That is then extracted and used to jar and make honey. All right? Let's see. So the plant determines, I'm sorry, I didn't finish this, the flavor, the color, the crystallization, so the functionality, and the pollen content, which is why the allergy thing, all right? Different amounts of pollen. So coming back to this fleck color, have you noticed that some honeys are really clear and some tend to be a little darker? The darker honeys have a stronger flavor. So if you don't like that really strong honey flavor, you might want to go for the lighter colored ones. Get that second one for me. Oh, stop. Thank you. All right, and then, okay. Let's see. The contents. Normally, honey is made of, it is 40% fructose, 35% glucose, and 2% sucrose, and 1 to 4% maltose. So someone who tells you, hey, honey's all fructose, diabetics can have it, are they right? No. All right. It's natural, though. Do you think the honey you get is natural? What do we call natural again? Okay, the honey that you get has been purified, unless you're getting it straight from somebody who's gone out and taken the comb himself and done this and put it in a homemade jar and given it to you. Your jars have been sterilized, the honey has been gone through, things have been gotten out of it, you know, like debris and little insect bits and maybe even little rat turds, which we find in everything. There's only so many parts per million of rat turds that are acceptable. And by the way, they are acceptable. You didn't know that, did you? All right, that tuna you eat, there's about, I think it's like 400 parts per million of rat turds are acceptable in canned tuna. Okay, I'm sitting here saying this, and I have a can of tuna for lunch. That's what I'm having today. All right. There are also greater than 180 other substances in honey. As you can imagine, these bees are not washing their feet before they come in the hive. They are not taking a shower and a bath and walking through a sterilization chamber. They're out flowing around, mixing and matching and rolling around with other bees and having a good time. So we see other substances in there would be like beeswax. We're actually going to get some wax. Other minerals, not so bad unless they're toxic minerals that we were meant to have, like mercury or lead, and water. There's also found quite naturally in bees Clostridium botulism, spores, which is why in food science we decided it was okay to purify your honey for you. You grateful? Mm-hmm. Now, could there be still some botulism spores in honey, even if we purified it? Yes, indeed. Therefore, honey is not recommended for children less than 1 year old. And I would go so far as to say, even as a dietitian, I wouldn't recommend it for compromised populations. Someone with we deal a lot with people with immune deficiency disorders, or can anyone think of a growing population in this nation that we would consider maybe compromised from an immune perspective?
Geriatrics.
The elderly, exactly right, geriatrics. None of you said that, but I'm going to say that you were guessing it in your heads. So, the geriatric population clearly would be possible. As a dietitian, I included in this, but the government only says not recommended for children less than 1 year old, and especially not for infants. What is an infant in nutrition science? How do we define an infant? 0 to 6 months, 0 to 6 months. And at that point, complementary feeding is introduced. Should we allow, you're a natural mom, you want them to have all this good stuff. Do you give them honey?
No.
No, no. Their immune system is not up to date, I mean, it's not fully developed. They shouldn't be having it. Okay, we are doing so well, y'all. We are now on to sugar alcohol. See? I wanted you all to gasp with excitement, but you didn't. All right, moving on to sugar alcohol. Let's see. Would you get that one for me, sweet pea?
Yeah.
You know what I need? Someone to devise a little hook for me. You know, and I can hook on that and bring it down. I am definitely height compromised. I think I should get some sort of, All right, so we're now on, we're still under nutritive, right? We're still under, this is the nutritive sugar category. Is everyone with me? We named sucrose and glucose, so that was the start of the nutritive. And then we talked about honey. And now we're talking about, we talked about syrups, then honey, and now we're talking about sugar alcohols. This is the last of the nutritive sweeteners that we're going to be discussing in here. Because I have had to, these are the most important ones. Alcohol. I haven't written that word out for so long, I always use the ETOH. All right, sugar alcohols. And these are essentially the counterparts of carbohydrates. And they're very popular because they're not non-caloric. They are not non-caloric, but they are low calorie. So, for example, if we look at sucrose, its sugar alcohol is sorbitol. And that is 2.6 calories per gram. What is sucrose's? 4, right? So it's cut it almost in half, the sugar alcohol. So you've almost reduced the calories by half if you use sorbitol. The mannose, mannitol, and I'm only going to use the ones that you guys see in the products that you buy now, is 1.6 calories per gram. 1.6. So it's more than half. Maltose, its counterpart is mannitol, and it is 2.1 calories per gram. And the last one I'm going to talk about, there's others, but you see this one a lot, is xylose, xylitol, and that is 2.4 calories per gram. And for those of you who are looking at the calories, you might say, well, why don't they all just go straight for the mannose? I mean, that's got the lowest calories. What you have to understand in food science, and I think you're starting to get it, is that there's so many other conditions you have to consider. It's functionality, it's taste, it's how it crystallizes, how it brown, whatever. There's so many things to take into just besides, let's pick the one that's got the lowest calories for the same sweetness. All right, these are found, quite frankly, naturally. They're found naturally in fruits and vegetables. Can I write veggies like that? Is that clear to everybody that does vegetables? But they're also made in the lab. They're synthesized in the laboratory by hydrogenating sugars. So I think we know, maybe you don't know this, and I shouldn't assume this, the functional group for an alcohol is an OH, a hydroxyl group. That's the functional group. So by hydrogenating, adding water to sugars, clearly we can create alcohols. These are significant not only because of the lower calorie, that's how they've been touted, their most important reason, but they're also resistant to the digestion and by our intestinal enzymes, which is why they have lower calories, because fewer of them can enter metabolism. That's what leads to the lower calories and their function in dietetic or diabetic foods. Have you guys seen that? For a while, the gum was a big deal. In fact, it still is. The gums that we chew, many of them, they have xylitol in them. Now, when you bite into, like my favorite is the extra. You ever had the extra gum? And I love the wintergreen flavor or whatever. You bite into it, do you feel all of a sudden a burst of coolness for a moment? That's the alcohol. Have you ever had a sore on your skin and your mom took up some alcohol and for a moment, though it burned, there was a cooling effect? You felt this burst of coolness for a moment? That's the alcohol. So when you bite into that gum, that's the slight release of that sugar alcohol, and that's why you get that coolness sensation in your mouth. They are also, from a food science perspective, humectants. What are humectants, you guys? Humectant. I buy little sometimes jars or cans. I have this closet that gets wet. It just is wet in there. It's just moldy. It wasn't Florida anyway. This closet is not here. And I would put this humectant, this jar of stuff, in the closet. What was it doing? It was absorbing. It was reacting with water and binding it. It was taking water out of the air and binding it. That's what humectants do. Good or bad?
Depends.
Exactly. It depends, doesn't it? It depends on what you're going for. In my closet, good. In many foods that I'm trying to develop, very good. Think about it. If I can bind water, what am I going to do? What do humectants do? Why would I use a humectant in a food? To reduce bacterial activity. Because bacteria needs water to grow. And I can dehydrate bacteria and kill them because they don't have water. So humectants are very important for extending shelf life of foods. Shelf life. Yes, ma'am. Sarah, you
I
have a
don't
question?
want to sound like I'm questioning you, but I googled it when you asked what a humectant was, and it says it's.
Are you supposed to have your phone out?
I'm using
Oh.
my computer to take notes.
Okay, you know what? We'll talk later, okay? I'm going right now by my texts and, all right? Okay? Okay? I don't want to confuse things right now, but I do want to know what you have to say, but if you don't mind, okay? So, humectants are going to decrease the moisture and therefore extend shelf life. All right? Yes, sir.
There's another term called desiccant that talks about like drawing things out. I think humectants kind of opposite.
You know what? I got these are my notes. Okay, right now, we're defining humectants as things that decrease the moisture. Okay? But I heard the word desiccant too. So I will look this up and I'll make sure I'm correct. All right, so thank you for that. But I have been teaching humectants. I would hate that I have taught a whole generation of food scientists that humectants work. I love you guys. Really do. Love Berkeley. Okay, so let's move on to, let's just start the non-nutritive sweeteners. Non-nutritive sweeteners. So we've been talking about nutritive sweeteners. And so clearly the non-nutritive sweeteners are not going to have much nutritional value. We're not talking about calories. So they're there for other reasons, okay, than necessarily adding nutritional value. And the first one we're going to talk about is aspartame. Aspartame. And the history of this is that this is the history, HX is how I abbreviate history, is in 1965, James Schlatter, some of you tell me how to pronounce this, Schlatter, how would you pronounce his name? Schlatter. I think it's school, Schlatter, I don't know. Anyway, he was researching, and by the way, this history that I'm giving you, I think it's interesting, but it also gives you perspective. Do I want you to know it? Yes. Because this is the basic intro to food science, and you need to know how some of these basic things were discovered. So, even if I'm not writing, you should be. He discovered this when he was working at producing ulcer pharmaceuticals, ulcer drugs. And he was working for a company called Searle. And they were famous for producing drugs for ulcers. And he was going to, the little pieces of weighing paper that you have in a laboratory that you put on a scale that you're going to measure out something, that little thing. He licked his finger. He's in the lab. Number one, big mistake you never do in a laboratory, is it? Anyway, he licked his finger to pick up the weighing paper to kind of, so it would stick to his finger. He tasted something sweet.
Oh.
And he's like, wait a minute. And he realized there had been an earlier spill, that he had gotten some of the powder on his hands. It was aspartame. And he's like, God, this is sweet. Tastes pretty good. And all of a sudden, they decided to market that. No. I love that story. So it is essentially asparagine plus phenylalanine, and you get this aspartame, which they have marketed as equal, that is 180 times sweeter than sucrose. From a food science perspective, 70% of all aspartame is used in soft drink manufacturing. 70%. The problem with aspartame, again, under food science perspective, heating of it. You can't cook with it. It reduces the sweetness. Why would heat reduce the sweetness if the combination of these two amino acids, by the way, one of them is non-essential, but it isn't the 20 we need. This one is essential. Why would heating cause this not to be sweet anymore? It's called denaturation, isn't it? Absolutely. It's going to break the bond, so they're not at aspartame anymore. So heating is not good for this. From a health perspective, there is no evidence. This is one of the most studied food additives in the world. I used it when I was pregnant with all three of my girls. Clearly, I felt very comfortable with the research. In fact, I was on a national television show supporting it, and Cyril sent me a lifetime supply of Equal. Because I couldn't be paid for it. The point, and I was facing off with a pediatric specialist. And I was saying, this is safe. I touted out all the research, and he was just like, yeah, but some of my patients get headaches. And I'm like, that's called anecdotal evidence, isn't it? That when we put, and Equal Cyril actually did a huge study of people who had headaches because they said they had Equal. So they gathered 4,000 of these people, and they put them into two groups. They all were headaches. They all said they had headaches after taking Equal. Put them in two groups. One group got Equal, one group got placebo. Guess which group reported more headaches? Placebo. And so from that study came the knowledge that people who tend to have headaches have some cluster behavior that has nothing to do necessarily with the food they eat. See you Wednesday.